Welcome to the office. We want to take a look at a couple of examples of homomorphisms. And really what we're interested in doing is looking at mappings and then verifying if they are or are not homomorphisms. All right. So let's let phi be a mapping from the real numbers to the integers under addition, given by phi of x is this thing. What is this? Well, this is what's called the floor function or the greatest integer function. Let me give some examples of this. What it does is it just takes the, calling it the greatest integer function. If I wanted to, I could say, what's the greatest integer that is less than 3.5? Well, that would be 3. Cool. Right, so greatest integer function, we can think of it that way. Or you might think of it as, hey, here's a level, here's a level, I'm right here, this is 3, this is 4. I'm between the two levels. If I drop to the floor, I'm down at 3. So we could call it the floor function, the floor of, I don't know, 7.6 is equal to 7. A couple that are interesting to know would be the floor of 5. It's the greatest integer less than or equal to. Okay, so this actually is 5. Okay, so we do have equality there. And let's see here. Another one that you want to keep in mind is negative 2.5. What's actually here that is another notation, and many textbooks actually do have the top line there, and some of them even have a second line as well, using the notation that we've presented here. The greatest integer less than negative 2.5 would be negative 3, of course, because we're looking at negative 2 is here, negative 3 is here, and I'm between. Drop down, then I'm going down to negative 3. So these are just some examples of the floor function. Hopefully you're familiar with that and you thought to yourself, wow, that was really boring. But if not, hey, there it is. So let phi be this, determine if that is a homomorphism. Well, it's pretty simple. We're just trying to decide if it preserves the operation or not. So let's take a look at an example. The floor of, let's go with 6.6 is equal to 6. And the floor of 2.4 is equal to 2. So what I want to do is I want to look at the floor of 6.6 plus 2.4. Well, 6.6 plus 2.4 is 9, and the floor of 9 is equal to 9. However, the floor of 6.6 plus the floor of 2.4 would be 6 plus 2, which is only 8. Of course, 9 is not equal to 8. Therefore, phi is not a homomorphism. So to try and make it absurdly clear, we're saying that we have an example where phi of A, B is not equal to phi of A, phi of B. Now, notice in our definition of homomorphism, it just assumes the notation of multiplication. Since we're working under addition, we used, of course, addition notation. We should understand these to be the same thing in the generalized understanding of the product notation, multiplication. All right, so one more example for this video. Let's let f be the additive group of all continuous functions mapping real numbers into real numbers. Let the real numbers be the additive groups, the additive group of real numbers. Excellent. So f is the additive group of continuous functions, and let r be the additive group of real numbers. So f is functions r to r. And now we want to talk about the mapping from f to r, given by the integral of the phi of the function is defined to be the integral from 0 to 4 of that function. So the image of this function is a number, right? When we evaluate an integral, we get a number. And the question is the operation preserved? So we're looking for addition and addition here. So I want to know, so what I want to do is I want to determine if phi of f plus g is equal to phi of f plus phi of g. That's what I want to do. I want to determine if. I don't know it yet. Let's determine. All right. So phi of f plus g is the integral from 0 to 4 of f plus g of x. Now remember, this is the appropriate notation in addition here. It's not f of x plus g of x. I mean, it will be, but the function f plus g is f plus g of x. So we want to make sure that we understand that this is the appropriate notation for this function in f. Now we understand this to be f of x plus g of x, right? We know that it is that, and we want to take advantage of that fact. But addition inside of the integral, right? The integral is linear, so I can separate it. This gives me the integral from 0 to 4 of f of x dx plus the integral from 0 to 4 of g of x dx. And of course, this is indeed what we were looking for, phi of f plus phi of g. Therefore, phi is a homomorphism. Excellent. And that's all that we wanted to show for now. We'll take a look at a couple more examples in our next video.